Hello, everyone. Nice to see so many of you turning out. I'm very glad to be here talking to you all the way from New Zealand. I will say from the outset, in fact, if you happen to catch any pictures of me, I can take back to the farm and prove that I was here. I'd actually greatly appreciate that. The topic I've got to talk about today is a pretty fashionable one, I think. We're going to be talking about how Reannz uses our network automation tooling to drive changes on our network and make sure that they're safe. I hope you'll agree I have a fresh spin on this, though, and that I don't have a fully realized solution to pitch you. I don't have some glamorously commercialized product. I've just got something slapped together by our operational team with a reasonably limited set of resources to work with. And it turns out, I also hope you'll agree, we can do quite a lot with that. Now, if I'm going to represent Reannz, there is one first question that always has to be addressed, and that is, what is that even? Reannz is an NREN, a National Research and Education Network. Our primary remit is to support academic research projects. NRENs come in all shapes and all sizes, and the remits often extend dramatically beyond that scope. In the case of Reannz, we do private WAN and internet services, wireless connectivity, such as you would find in a commercial telco. As part of government, we also do some work in public services. We use our identity management system to support the rollout of public Wi-Fi networks for digital equity projects. And in breaking news, we've just taken on some lovely people who have brought along a high-performance computing platform, which is very exciting. Please don't ask me any questions about that just yet, though. I do have some smoke bombs in my pocket. In fact, if that happens, I need to make a quick escape. I cannot talk about NREN, of course, without talking about the wonderful global community that we are a part of as well. There are about 120 of these organizations all working towards this common goal of supporting research. I know the more cynical among you, well, this is a tech conference, I suppose I should say all of you. All of you are probably seeing already all of the pointless meetings that you can make out of all the permutations of these multinational organizations. But I assure you, this is not the United Nations. There are very tangible benefits from these relationships. I won't linger on that subject, in fact, as I normally would, only because I see the program promises we'll be hearing from Pete Stamp tomorrow from your local NREN ARNet, and I'm sure that he'll do a terrific job waving the flag. Now, since I'm going to be talking about changes, let's go back and have a look at some changes past, shall we? Reannz was established in 2006. We're pretty young for an NREN. The earliest view of our network I had to show you, though, was from 2008, and it looks like this. We had a ring switching topology, and at this point we actually did only provide NREN connectivity. If there were resources within that community, we would help you get there. If you wanted an internet service or anything as simple as that even, we would say that's out of scope and you need to go find a commercial telco to provide that for you. The first major shakeup came in 2013 when our operating model changed quite significantly. We partnered with a local telco called FX Networks before they dumped us and ran away to another company you might have heard of called Vocus. Under this model, we would own outright actually a share of their optical platform, and we'd work together as a kind of public-private partnership to support these research initiatives. In this case, our presentation of the network looked a bit like this, and we still have our ring switching topology actually, though I gather at this point they were moved on to Brocade hardware rather than the initial extreme kit that pioneered all of that. This is all still very unrecognizable to me since I've come onto Reannz today. In 2018, we completed an upgrade onto our 100 gig backhaul run off of Juniper gear, and this is what that looks like. You can see we've expanded our presence pretty significantly by now. There is no more kind of Metro Ethernet going on. This is now an MPLS network, so things have considerably changed now, as you can see. And my last state of the network to show you is from the present day. I think I grabbed this animation from this weekend, in fact. And this is where we landed after our most recent round of hardware refreshes, which we completed this year, and which is going to be the case study that I had to share with you today. Now, alongside all of these changes that were occurring on the network, we had a parallel journey going on as we developed our network automation tooling. Now, the first stage in this process I can describe really quite simply. The Reannz network was, from the period 2006 to 2014, built entirely hand-built to order. So there was no enforcement of any kind of standard architecture. Whatever an engineer wanted to do, he could slap straight onto the network, and there was no sanity checking of any kind, so we had to just trust in this person's wisdom. At a certain point in my career, I'm sure I would have responded to critics who talked about those kind of risks by simply saying they just don't understand my art. This isn't dubious config just flung haphazardly at the network. This has love and attention. It's hand-built craftsmanship like a luxury car. Those critics might reasonably rebut, though, that those things notoriously don't really work very reliably. So if you'd like to make the same argument, I'd suggest perhaps you find a better simile than that. Over time, we did start to recognize the need for some scripting to enforce some good sense on our network, and we started developing scripts independently as one-offs to address that need. Some examples of such are VPLS and MPLS device meshing, member RPF filters for anti-spoofing, routing policy controlling what announcements we send to various upstream providers, and standard firewall policy that we push across, where we push the same policy across the same device platform everywhere. And there are some ways that things such as these lend themselves very well to scripting. They're very repeatable. They abide by a very consistent set of logic that you can easily code and easily gain the advantage of the scripting without much initial investment in setting that up. They're also very error prone. They rely on quite granular configuration, and you have to get every line correct or you will run into trouble. And when you do, they also have potentially a very big blast radius. If you get this wrong, you might be self-inflicting a denial of service. You get your firewall policy wrong, you might start leaking personally identifiable private information from your customers as well. And I gather that's something that's also quite frowned upon. Now, the problem at this stage is that every script has to reinvent the wheel. They're all trying to figure out how to parse our network configuration in order to interact with the features they need. And every time we push configuration out that it doesn't understand, sometimes we just blow up all the scripts. So that imposes a maintenance burden that's a bit inconvenient. In a similar way, they have to figure out how to interact with the APIs that govern all our databases, controlling allocation of network resources like IP addressing, BGP ASNs and such as well. So we really want this generalized. We do it right. We do it once. Before we can do that, though, obviously we need to choose a suitable mascot for the system. Something we confident represents the values of the IT community. There's only one option, as I see it. Something that has a computational mind, a get it done attitude, and probably a crippling dependency to alcohol. That is how we got Bender introduced to us. This is our mono repository now of all of our automation tooling. Bender began life as a parser. We just wanted to split out that element of what we needed, strip out everything from the network, slurp it all up, and just get a state that we could work off of any of the other tooling that we had. We noticed when we had that as well, we could also lint through that and discover a lot of the things we didn't really like about the config on the network. A lot of config that was sitting around stale for some old, now unknown purpose, or things that just were implemented in a way that we now don't like and would like to tidy up. So that was all very helpful. We also started rolling out the generation of new config to within this tooling as well, for a reason I'll show you with this workflow here. So as I said, the network device configuration is currently our source of truth. Everything that produces the current state for this automation model is slurped up out of there. And there are compromises that come with that, which hopefully, if I'm managing my time correctly, I'll come to speak on, but I'll just say that much for now. So we look for all of it to produce this current state of the model. Our engineers can then introduce with Bender CLI tooling to produce new config, and with that, they now have a picture of the future state of the network as well. So it makes sense to keep these things together. When you have the current state and the future state together, that lets you produce a diff. And that's what happens when we use apply config tooling to try to push configuration out to the network. It spits a diff back to the engineer, and they then approve yes or no, do I want to actually do this to our network? We have no automation tooling as it stands today that independently does anything. Everything is accountable to some particular engineer. And as I said, we have the separate workflow that broke off of this, where we can lint through that state that we've gathered and spit out any questionable config that we see out into alerting, whether that's because it's incomplete or we just generally think it doesn't abide by the architecture that we've agreed as standard. That's a bit like monitoring, although monitoring would query the network devices themselves, of course. These netlink checks actually just run against the model, and then it handles alerts in a very similar way. It's just pushed out into the same system where our engineers can triage it as a fault, effectively. So that brings us to the subject of our hardware refresh. This is the tip of the spear before our storeroom was overrun with all of our new devices. I do find it's very helpful to keep pictures like this around, just for when I'm melodramatically complaining to anyone foolish enough to stop and listen about my workload. And it looked a bit something like this. We were blessed in this instance that we would be keeping the same vendor, and there's a lot of convenience that comes with that, but it was going to be a quite different deployment with the same vendor. Our goals here were largely about increasing capacity. We wanted to go up to potentially 400 gig, and we wanted a lot more port density on the way to get there as well. We also wanted to experiment with some more cutting-edge features like hierarchical QoS or segment routing as well. So there was quite a lot that went into this brief. And naturally, as with any enterprise, we didn't feel like spending a lot of money. So that was another thing we forced the vendors to keep in mind. And we landed on a model something like this. We no longer have this kind of complete chassis with line cards to produce a single routing platform, but we'd instead split it off across a lot of independent chassis. So you can see here a couple of options we have now for provider edge routers, and a couple of options for border routers as well, and we would install this in some combination everywhere that we were present. Here's an example that's not terribly remarkable in any way. We've got our big MX480 routing platform there with some 10 gig mix, 1 gig mix, and it looks like some 100 gig interfaces up there at the top, and we've just picked up all of that and moved it across to a model that now looks something like this instead. To complete this deployment, this is effectively how we planned it to go. We were hoping to have all the configurations applied to be 97% generated by code. I don't have data to support this, but I think as we iterated on this process as time went by, we did land somewhere in the ballpark of that number, to suggest that for every 100 lines of config would either have to be produced by an engineer or edited in some fashion from what the generator produced. That generated config would be reviewed first of all by the engineer that produced it, and then by a second set of eyes as part of our standard process. When it came time to do the migration, we would have one engineer on site, and we would have another engineer leading the change remotely from his laptop. We'd have 3-hour change windows, and of course, if that time's not enough, that would simply mean that we'd spread over multiple nights. We'd target to have 8 to 12 member handovers migrated per night, and that was decided somewhat arbitrarily at the discretion of the engineers running the change. Now to the problem to be solved. When we're doing a big project like this, the difficulty we have is in ascertaining if the network service is continuing to function after we've migrated it completely as expected. And there's actually a lot that goes into that. The immediate answer is perhaps, well, why can't you just use monitoring? Why can't monitoring tell you when something's broken that was working before? And it can to an extent, but it has some issues. As currently implemented by Reannz, our monitoring is very interface aware. If we pick something up and we move it, monitoring sees that a bunch of stuff has gone down over here, and it's going to complain about that, which is not terribly helpful. It will see a lot of new services arrive somewhere else as well, and eventually when all of our cron jobs are run, that will be fit into monitoring too. But that's not really what we're looking for. Monitoring also lacks a lot of context. There are some things that might evidence a fault in this context especially, but might not be a problem in the normal working order of the network. For instance, if some routes are withdrawn off of a BGP handover, that's not an emergency in itself. The users of this service, it's their prerogative if they want to stop announcing some prefixes, that's fine. But if this happens to occur while we're in the middle of futzing about with hardware, that's something we should be paying attention to. We need a system to deal with that. Even basic handovers, it turns out, it's pretty time consuming to go through everything that you might possibly have to check, and it's quite error prone if there's just such a great volume of information that you have to pour over. So we developed some state check tooling to help. This was intended to automate gathering state related to the interface before and after the migration, and present back any changes to the engineer to triage into action. The goal here is that the engineer's focus is drawn specifically to where we think there are areas of configuration that might be wrong. So what kind of things are we looking at? If you've got a physical interface, you know the kind of things. We're going to be looking at the link state first of all. If it never comes up, that's probably a bad sign. If we've got MTU mismatches, that's never good. We're going to be looking at traffic patterns. We're going to be looking at optical information off the DOM of the transceiver, that kind of thing. VLAN interfaces add some new things to worry about. We've got push-pop operations going on for Q&Q. We've got EVPN multi-homing. Obviously, you don't want to be blocking on both sides of a multi-homed EVPN, nor do we want to be affording on both sides of a multi-homed EVPN and create a broadcast storm. We've got BFD sessions needing to remain up. And we've got our dynamic routing protocols. If you've got a BGP handover, we want to know that that continues to be established and continues to exchange routes as expected. And OSPF adjacencies, of course, continue to complete the exchange of those BPDU databases. Now, fortunately, we had a simple test we could use actually everywhere that we were present. There is a project originating within the NREN community called Persona. And it speaks to the problem we actually heard a little bit about from David a moment ago about getting information from your upstream providers. I'm sure that you all have very comprehensive monitoring of your own environment, and I'm sure you're all very frustrated sometimes when there's an issue upstream that's causing you problems, and the providers are just not nearly as interested in that as you are. So the Persona project is a network measurement toolkit that can be deployed on servers, and there are thousands of these around the world deployed by Reannz and universities and some private providers. And happily for our purposes today, in terms of their network connectivity, they are absolutely dirt simple. You just point them at the internet and you're away. So that gives us something very simple we can test to prove the concept is working every time that we start a migration. Find the Persona node, see that we can cut that over onto the new devices, and if that's working, if that's accessible on the public internet and doing everything it should, we're ready to go ahead with the migration of the customer services. When we generate config, we get out some YAML that looks a bit like this. It tells us what the before state and the after state is of any services that it finds. And in this case, it's all very simple. You've got a physical interface and you've got a VLAN on there facing out to the internet. Based on that, when we're ready to get started, we can run a state gather, and it'll automatically go through and collect some of this information based on the parameters that were recorded in that YAML. Like in this instance, it looks to the original device there, AND16, that is Advanced Network Device, in a not terribly illuminating naming convention of the time. And you can see in this output, you can get all of that information that you need. You've got the link state, you've got the MTUs, you've got all the auto negotiation parameters and such that you might like to pick out of there. Same on the VLAN interface. You've just got a simple link net out to the internet. You've got your diagnostics off the DOM there. I can see we've got good light to start. We should hopefully have good light when we're finished. And then we look a little bit deeper as well to get a sense of the traffic patterns and see maybe if something's changed when we're finished there. Then when we're done, we just do it all again. We run a compare. It goes through and collects the dump of the same information off the new device. In this case, this service has been migrated off of the old AND16 onto netmupd01, and we look for all those parameters we've been looking into. We go through all of this. I look here. I say yes. I've got my light readings as they should be. I've got my traffic patterns, ingress and egress is all fine. That's great. And then we can make a conclusion: is the surface working as expected? In the case of something as simple as this, I hope to just see returned an empty diff that says everything is as everything was. Now, if I were to do this manually, that's the process I would have to follow. I'd have to go through, log on to all these devices and run all these show commands, probably twice, because I'm convinced that I'm an expert touch typist, despite all available evidence. And then I'd have to go down my checklist and check out all of these options one by one. I can do that quite reliably, I think. There's nothing too complicated going on here. It would take me maybe 5 minutes to do that. The tool did it instantly, though. So right away, we have saved about 5 minutes per migration. But I hope actually to have a conclusion that's a bit more dramatic than that, as in the case of my next example. Look upon my works in despair. This is one of the Reannz member networks that I've built, scrubbed of anything identifying, and you can see it's a bit nightmarish. This is the logical routing topology as far as I could represent it. There is some details missing that I thought would just confuse things. But effectively, you can see we've got 24 private VRFs here, all being... oh dear. Can I get this back? Let's see. Oh, it's not. Oh, there we go. That's perfect. So we've got 24 private VRFs all being routed through geographically redundant firewall stacks onto multiple border VRFs. We've then got private handovers to multiple different cloud providers. We've got a Reannz internet service. We've got connectivity onto different NREN resources. And all of this tends to be implemented in a pretty complicated way as well. So I guess my question to you is to take a moment and try to imagine what you would have to go through to actually verify that everything here is working as expected after you've been messing with something on here. It's pretty considerable, as you'll see. The same kind of YAML comes out when we generated the config for this. You can see, as before, we've got an interface, we've got a VLAN, that's all fine. We've got a bit more now this time as well. We've got a VRF that needs to get built. We've got a BGP neighbor that needs to be stood up. Got some more VLANs, so we've got an EVPN now as well, so we're looking at layer 2s, and if we look down to the 27th item there, it looks like we've got no SPF adjacency to worry about as well. And I could scroll and scroll and scroll forever through this YAML, because it turns out it was actually amounting to 1,525 lines in total in the end, just describing the services that Ron must hand over to be moved, and none of the details of such, except just this is it. I would like to go through now and show you all those show commands as well, but I imagine that the next 6 presenters probably don't want to give up their time while we trawl through all of that. So I have the summary off of my Vim session instead, just to show off the line count. We had 50,000 lines of state gathered from the before and 50,000 lines of state gathered after to describe one member handover that we were migrating during one of these moves. I will add one more note to this as well. This is an extremely high availability network. If there is a problem on it, it is already past the deadline to be solved. You cannot have anything go wrong in this as well. You have to be perfect. So I don't really like much of that at all. Let's hope the scripting can help us out. This is what happens when we ran our state compare. It wasn't quite instant in this case, I will admit. The time it takes for all these different calls against the devices to be processed does add up a bit. It probably takes 3 or 4 minutes for all of this to come out. But when it did, all of that change, all of those 50,000 lines we would have had to review are reduced to just this. And I can triage a lot of this very simply. The first 2 things that were noted, for instance, are some possibly strange traffic patterns, and that where the output and then the input has changed in some dramatic fashion that apparently warrants my attention. But I know enough about this network to know that that's just part of the normal ebb and flow. We've got bidirectional traffic. It's functioning effectively as I expect. I can move straight on from there. Third one's a bit different. Input and output packet 0. That 0 stands out always as a red flag to me, so I'm going to put a pin in that one, and we'll come back to that. Going from 0 to 2 doesn't bother me. I can imagine a context where that matters, but it's not this one. I know how the network works, and that's completely fine. Same with the VRF state that's changed. We've got a management loop pack that's on a new address now. That's per plan. Obviously, if we're moving from a single chassis to a collection of multiple in a location, sometimes we actually need multiple management addresses now. So it doesn't make sense to try to preserve the original one onto the new build. And then one more example of traffic patterns changing, which doesn't concern me so much. So after all of that, there's only really one thing that I need to dive into, and that's why we don't see frames incrementing on this particular VLAN. There's a couple of ways I can look into that. I can just go and look on the interface to see what counters are incrementing over time, and hopefully it will sort itself out. I can do a packet capture, or I can run this tool again and just see if anything's changed. And in this case, it's nothing more than the fact that this VLAN just happens to be quite quiet, and we just hadn't yet observed any frames across it. Wait a couple of minutes, but that's no longer an issue. We've got the evidence we need to suggest this is all working. So I was a little bit worried about this migration, honestly, for some of the reasons that I've just said. But all in all, it was over in 10 minutes, 0 problems. We whipped straight through, and I was very, very pleased about that. Now, you may think it was slightly disingenuous, though, how I presented this, in that you don't necessarily need to go through all of those 50,000 lines of state and tick everything off on a checkbox, because obviously it is possible to reason through when something is broken and troubleshoot and more surgically look for what actually needs to change or what you need to pay attention to. And I've got a couple of examples there. In this case, the diff has turned out that there was an interface that was up, used to be down, excuse me, the other way. We had an interface that was up that is now down, or we had a BGP handover that used to have an established peering and is now struggling to connect. These are very obvious issues. I don't want you to go away from this conference with the impression that I'm some kind of braggart, but I do feel very comfortable that I can figure out the green thing that is now red needs some attention. I'm happy with that. But I have some other examples that is much less the case. Here's another case where we had input packets not accumulating on the interface counters. Last time that wasn't a problem. We just had to wait a little bit and it came up. But you can see there's a little bit more activity on this interface, and it's not the case here. We actually had some trouble with Ethernet auto negotiation between our platform and the router of our member that we were connecting to. On our side, the router was happy. It said link was up, there's no faults of any kind. So you might be inclined, if you're doing this all manually, to move on. It's a simple service and it says it's up. Let's not linger. But if you looked on the other side, where we didn't have visibility, things would have been very wrong. And it's very fortunate, actually, that the script was able to recognize that and point us to say, maybe actually have a closer look at this and make sure that it's capable of accepting ingress frames. So we can credit the tooling for helping there, and also in something like this. I've got a BGP handover, and it's dropped a few prefixes, which I mentioned before might be fine. Announcements get withdrawn over the BGP handover. I'm not necessarily bothered by that. But in this context, I am. Actually, diving into this, we found that an import policy had been misconfigured, or referenced incorrectly, and we had dropped a few routes of this handover for that reason. That's not great. Definitely something that needed to be fixed, and fortunately, with the assistance of this tooling, we were able to do so. And then one more example where we see a major step change in optical levels after a fiber's been repatched onto a new device. This one I think would have been picked up simply because the warning threshold on this device was -15 flat, and we've only just dipped under that. So that would have simply spat out straight into our alerting, and that would have been fine. But if we imagine instead that it had been -14.99 instead, there's no alerting to help, and probably we would have just seen interface up bidirectional traffic. That's great, let's move on. And then we would have come back a week later and gone, this interface has errors accumulating, I hate this, why didn't we do something about this last week? Or worse, the member contacts us to say, why is the service that we're paying for suddenly terrible? So yeah, I would say that the tooling on each of these migrations we did probably contributed about 3 or 4 high-risk scenarios for us to look at, and we have to give it some credit that it's helped us to avoid some outages, some disruption that would otherwise have occurred. Now, if we are to commit commit resources to this project, we must have a full account. So let's take a look if there's anything we can blame the tooling for as well, if we got too complacent with all of this help and cause an issue that way. So we're going to look actually at the things that have gone wrong, and the first thing was this. We had an independent domain BGP attribute emitted from the private WAN, a private WAN VRF, which caused some BGP loop detection to kick in and suppress some active routes. And this one can be answered quite simply, and that it was the first migration we were completing, and the tooling actually wasn't ready to be deployed yet. So we cannot blame the tooling when we didn't even have it. The reason we did this is because there was a hardware failure in this POP that was going to require some disruption to attend to anyway, so we thought, let's just plow ahead with the migration. We put our best engineers on the case. They worked for a few weeks very diligently to try to make sure there was no issues. They accounted for themselves very, very well. I think they did a terrific job, and yet I'm here talking about it anyway as a failure. So this is our benchmark, I guess. If we don't have tooling, this is what happens. Next is an incident. There was an MTU emitted with the creation of a backhaul circuit, which caused localized isolation of a remote region in New Zealand. It's obviously not great. Can we blame the tooling? Answer, no. The tooling actually was available to generate this config correctly, and the engineer chose not to use it. So if you're working on this kind of project, that's something you will have to be aware of, you might not have considered. It's not all about the technical implementation. You do have to advocate as well. People are stressed. If something goes wrong, they will fall back on what they know and not the tool that you've provided them they don't fully understand, even if it's perfect and wonderful and you've done everything right. So keep that in mind. You might have to advocate a bit for yourself. And then lastly, there was a case where BGP configuration was submitted for a long-line internet service downstream of one of our devices. We had a rare kind of service that we offered where we would be present in the DC beyond the scope of our MPLS mesh, and we would drag some services back with a simple bridge onto an internet router. And the problem is our model for generating config assumed we'd have an interface on one side to pick up and move to another one. And in this case, there's no interface. There's just a VLAN that gets bridged into the internet router. So we figured adapting the tooling for this is a bit of work, and it doesn't come up very often, and the tooling won't be of much use going forward, so we'll skip it, and we'll just trust people to build the config manually correctly. Obviously, that backfired immediately. Some people have to just ruin everything for everyone. Even in a case as simple as this, where making a mistake makes you a bad engineer or a bad person. Yeah, well, sometimes who looked a bit like Darwinian man to start just turns out to be a well-groomed ape in the end. I would like to say a few words in my defense, though, how I managed to mess this up. There was a bit of time pressure introduced by the DC operators we weren't expecting, at the same time as we were trying to troubleshoot a software bug we had run into. So just a slight bit stressed, and in that context, I just forgot to actually apply this config. So that was my fault, and I tried very hard, but I couldn't find a way to blame the tooling for that, unfortunately. And that's it, in fact. Nothing I can blame the tooling for. It did a terrific job, and it helped us to limit the disruption for our membership. And just one thing quickly before we move on, does that mean our journey is over? And the answer is no. There are some limitations still with the model. One of those is difficulty enforcing standard architectures. We've got some tests to check whether the config we're rolling out makes sense, but we have to anticipate what that is. People are always coming up with new and creative ways to do things that we don't like. It'd be nice to have a single platform from which we can view everything and keep visibility of all of that. Having the network as a source of truth is not helpful if it means we have to keep all of our service enriching metadata for services within the confines of that config. The more things we want to do to track different services for reporting and such and marry them up with each other, the more we have to try to squeeze into that config, and it's quite tricky to do that. Resource management doesn't really work as well with this model. If I go through all the trouble to allocate myself a BGP ASN number and document it perfectly what it's going to be for and where it's going to be used, and then I go to use it and find that somebody's already just slapped it onto the network without doing any of that, well, their work is going to win because it's now on a live production service, and I'm just going to have to go back and do my stuff again. So I would really prefer that all of that happens as part of the generation and before the config goes out onto the network. And lastly, it is network-centric and not service-centric. We're talking a lot about VLANs and interfaces and such, but the users of this service don't necessarily care about those things. They have something they want to use their network for, and they want to hear the story in that context. The context gets lost when we spit these things out onto the network, though. If we want to know what these things are for, we usually have to go and ask the engineer that set it up what they've been talking about with the customers and hope that they remember. It'd be nice if we could bake that into how we're configuring things. So we're developing an automation platform. It's going to have a sense of intent instead of trying to reverse engineer that from the network config. It will consist of an orchestration layer that will be present to manage the lifecycle of the service from its deployment through to its retirement. And it will enforce configuration templates when it communicates down to the configuration layer to push this config. We will always allow custom configuration. It's very important that we can do for our membership whatever they need, but we want to have somewhere where that is always visible. Thank you very much for your time. Thank you, organisers. I'm sorry, I think I overran just a little bit. Questions, anyone?